So this is where we're going to end up applying the quantum numbers, and hopefully they'll make more sense. What will help to have on you at the same time when you're going through the PowerPoint or watching this perhaps would be a piece of scrap paper so we can kind of do examples together, as well as a periodic table. Remember that there's one saved to our home page, so that's the one that I will be using and referencing. So electron configuration is the way that we're going to show pretty much how the electrons are put into these quantum numbers. So we know that 2 go into each orbital, but each orbital has, except for s, different orientations, and we have different n values. So I kind of promised you we wouldn't have to draw them like we used to for Bohr diagrams, but we're going to have to show all of this stuff in a different way, and that's where electron configuration comes in. So what it pretty much shows us is electron arrangement within orbitals. We call it shorthand. It's obviously much easier than drawing a whole bunch of spheres and weird propeller looking shapes and trying to figure out how to overlap all those. By the time you do a whole bunch of them, it probably won't feel very shorthand, and we will have a shorter way to actually do it. So there are a few different ways to kind of get this information communicated to someone else. So we can do an energy level diagram, which is the most complex way. We can do a complete electron configuration, which will then seem much simplified in comparison. And if you do too many of those, it will also seem like it's very repetitive. So the next way, and the easiest way that after you do it quite a bit and you get more comfortable with it, is typically what you'll see, and it's called the noble gas configuration, or a condensed version of electron configuration. For the most part, I'll never make you do some of each one. I kind of want to make it up to you which ones you feel you're most comfortable with. So if you do enough of the homework and if you do enough of your own research, or perhaps you've done this course before, maybe noble gas is the one for you. If you like seeing the greater picture, energy level diagrams might be more your thing. Doesn't really matter. So let's learn about all three of those. So energy level diagrams, we've already kind of mentioned, and we've seen an energy level diagram actually in the last slideshow, that as we go up in principal number in n value, we're getting greater and greater energy levels. So depending on the way you read energy level diagrams, sometimes it will show you that. Another thing just to point out before we get into energy level diagrams is that all of these are during ground state. So yes, we know that we can energize electrons, and maybe something that was at one point in time in a 2s might jump to a 3s, but we're always going to do it in ground state. Anyways, so we've got a few different rules coming at us. So we did already see in the last PowerPoint Pauli exclusion principle. We're going to build a few more rules in this one. So this is pronounced off-bow principle. And what it's pretty much telling us is we're always going to fill orbitals from the lowest energy to increasing energies. And we can't just start filling an orbital at the 2p level without first filling up the 1s and the 2s. So that's what off-bow means to us. We're always going to add electrons in increasing energy levels, still making sure that each level, or each orbital, sorry, gets 2 electrons total before we move to the next. So we might think that because we saw some smaller stuff, that would make a very easy process of always going from 1s to 2s to 3s, and that would make a lot of sense. But we do have a few things that are a little bit strange, and perhaps this might be a very, very helpful slide for you to come back to. Because when we were looking at magnesium in the last PowerPoint, we did follow that trend. We followed that we did 1s first, then 2s was second closest, followed by 2p, and then we saw 3s. We also have 3p's. We know we have 3d's. We saw them in the last PowerPoint. But 4s, despite being a larger n value, actually has less energy than the 3d's. So you'll see some weird anomalies where we don't actually go in numerical order. It will be helpful to look at a periodic table with this, because the periodic table will be like a little bit of a savior for it. If you also want to use these, you are more than welcome to, because these are also helpful. This one more so. So just to keep in mind that off-bow principle means we're going in increasing energy levels that we're filling, and that might not always mean that we're going from 3s to 4s, because then we've got some kind of outliers sometimes. So don't worry, this will pop up on the periodic table for us to not have to actually memorize a thing either. So either using your periodic table or these guys will know how to fill stuff. We're just showing, by the way, on this side how many different orbital orientations we have. And that's why we only have 1 circle for S's, 3 for P's to show us that there are 3 different orientations, 5 for D's, and 7 for F's. Okay, so that was off-Bow's principle. We're looking at energy. Just to get all this stuff out of the way, we also have Hund's rule. So Hund's rule, what we typically think of is this analogy, the bus seat rule. So the word analogy is going to come up in your assignment. Analogy just means pretty much like a simplified way to communicate like a difficult idea for our chemistry's sake, just by comparing it to something in the real world. So Hund's rule, if we just talk about electrons, we'll understand it, I'm sure, but an easier way is to call it the bus seat rule, especially now with COVID. But before, say you're riding the public bus to school and you get on the bus and there's someone in each 2-person seat, but there's one on its own with absolutely no one sitting there. Odds are that you're going to sit in that 2-person seat that no one else is occupying at the time, instead of pairing off with a stranger that you don't want to talk to. So that's what Hund's rule pretty much is, but for different orientations of an orbital. So that if we were to have 3 different p orbitals in the exact same n, so they're all 2p's, each one of those orientations is going to get 1 electron before doubling up has to happen with the 4th electron. They would also all be in the same spin direction. So remember we had that plus half and minus half at the end of the last PowerPoint? They would all pretty much be plus halves. And then when we start double occupying, they would switch spin directions. And we'd start adding those minus halves. So that's what Hund's rule is. Pretty much called the bus seat rule most of the time. So here we have an energy level diagram is taking into account both off-bow and Hund's rule. So off-bow is coming into play because we filled up all the 1s before we filled up all the 2s before even touching the 2p. So we're going increasing energy levels. Hund's rule doesn't really apply to the s because we've only got 1 orientation, right? We have to pretty much fill all this 1s in its own orientation before we can get the 2s. But once we have different orientations, once we have p's, d's, and f's, that's where Hund's rule comes in. They're going to singularly occupy different orientations, and each one of these boxes is trying to show us a different orientation for that orbital until we have to have 2 in the same orientation. all of these are in the same spin, and I remember saying something about we're going to show spin in a different way. So a lot of the time spin is shown by arrows, where you're going to have like an arrow pointing up showing us a positive spin, and an arrow pointing down, which is going to show us a negative spin. So before doubly occupying, they all have the same spin, and if I were to need a fourth arrow, a fourth electron, it would go into this first box and point downwards to have an opposite spin. So if each one of these arrows is an electron, and we have 1, 2, 3, 4, 5, 6, 7 electrons, we are going to have element number 7, as well as long as we presume there's no charge, and this is going to be the electron configuration for nitrogen. Cool. So that's showing it through an energy level diagram. Lots of things to show. We're getting like all of our information thrown out there. More energy level diagrams. So the total number of electrons should be the same number of arrows we have. Positive direction going up for spin, negative going down. We'll see that we'll never have two in the exact same direction. One's up, one's down. We're always filling 1s first. That's what off-bow told us. It's the lowest energy before we work up to something that's higher energy, the 2s. And if we were to follow that off-bow slide, this one up here, after 2s comes 2p, and if we fill all those, comes 3s. As we're filling something that has several different orientations, they're always pointing in the same direction, and we aren't overlapping the same orientation orbital. These guys got their separate bus seats. These guys got their separate bus seats. This is a terrible slide because we don't see them overlap. We go straight to neon, which also should be a lowercase e. And it shows us now that we're going in the opposite direction. Cool. That's our different spin numbers for our quantum numbers. And then if we needed to add an extra electron after filling out all the 2s's, we can't shove a third one in anywhere. We're going to have to bring in the 3s and put it into its own orbital. So an orbital can have 2 electrons or fewer. It doesn't have to have 2 electrons. It might just have one buzzing around. So there is our energy level diagram for a whole bunch of different elements. The arrows will also equal what element number we've got going. It's a lot of work to draw all of this. So you're probably looking at this electron configuration instead, which is our second way of doing things, which will be a little bit easier. It kind of summarizes stuff without looking at spin. So it will say we have 1s with 2 electrons in it, and we give it a superscript. We have our 2s orbital with 1 electron in it, so we give it a superscript of 1. So we're kind of summarizing how many electrons we have in the entire system, the 6 here, instead of blocking them out into the different orientations. So that's going to be our second way. I'm getting ahead of myself right now because we've got one more slide first. So let's see which one's the correct way. We've got 1, 2, 3, 4, 5, 6 electrons. So we have 6 electrons. We're looking at element number 6, carbon. Would carbon either be this one on the left or this one on the right? Well, we're seeing that the only difference is that by the time we get to the 2p's, these ones have their own orbital without sharing, versus this one, which would be like if you were sitting on the bus and a perfect stranger came and sat next to you despite having 2 empty seats. It should be very weird. So this one's definitely right, right? It's following Hund's rule. Also both following off-bow, right? Is there anything wrong with the second one? We've got 1s, 2s, 2p, 3s, 3p. If we went back to slide 5, we'll see that that is following off bow because these are going in increasing energy, which is awesome. We've got one up, one down, one up, one down, same thing, one up. It all looks perfect. So let's just see what element we're actually dealing with. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in the 3p. We've got 13, we've got aluminum. So not to get ahead of myself too much, but obviously 13 electrons isn't a heck of a lot to count. And it might get wildly harder. There's also another way to simplify that for you based on the periodic table. So the fact that we know there's one electron in 3p, we could very easily figure out which element we're looking at. Anyways, without going there yet, let's look at electron configuration and drawing them like a very big line of numbers and letters with superscripts. So here is what we kind of saw on the slide 2 slides back. So we're going to do it a little bit more condensed by showing up front what our principal number is, the n. In the middle, the letter for what shape of orbital we have. So we've kind of seen this stuff so far before. The only new thing really is the superscript. And what the superscript is trying to tell us is how many electrons are within that orbital system for the 3p's. So we know p's, there's 3 different orientations. All can hold 2 electrons, so p's can hold up to 6 total. This number would have to be 6 or smaller. So 5 is perfectly fine. It just means one of the orientations isn't fully filled. S's we know only have one orientation. That one orientation can only hold 2 electrons. So if we were to have an S with a superscript, that superscript can't be anything higher than a 2. And then it'd be different for D's and F's. So let's look at how this works. I've kind of said it multiple times that electron configuration is going to follow kind of a trend on your periodic table. So you don't have to really memorize too much, but it still takes a little bit of work to make sure that you can use your periodic table effectively. So what we call them pretty much are blocks. So we've got our S blocks, we've got our P blocks with a little bit of S block going on over there. We've got our D blocks, and we have our F block. And this follows the shape of our periodic table. So we have our S's down the first 2 columns. We know that S's can hold 2 electrons total because there's only one orientation. So that's very cool for us to know that this is S blocks, because we'd know this would be like a 1s with a superscript 1. Helium would be a 1s with a superscript 2, because now we've got 2 electrons for helium, right? Our principal number would get bigger as we go down. We've got the 2 S's, 2s1, 2s2, 3 S's, 4 S's, 5, 6, 7 S, 7s2. That's our S block. Cool. And we know that the S is L value of 0, and it starts for n equals 1. The P's don't come into play until we have an n of 2, because we know it's that n minus 1 from the last PowerPoint. So that's why when I go back, we don't have a 1p, we start with 2p's. And we'll start with 2p, 3p, 4p, 5p, 6p. And we know we have 3 different orientations of p. Each orientation can hold 2 electrons. And we said on the last slide, that means our superscript can only go up to 6. So if we went back to our periodic table, the p block is 1, 2, 3, 4, 5, 6. Awesome. Elements deep. So if this is 2p, Ne would be 2p6, Ar would be 3p6, 4p6, 5p6, 6p6. Or if we just want to look at something kind of somewhere in the center, we know this is 2p, this is 3p, this would be 3p, 1, 2, 3, 4. Sulfur would be 3p4. Cool. So there is an easy way to see kind of where your configuration is going to end. And that's why I said when we found out aluminum before that there would be an easy way without counting all those electrons to know, because we finished our configuration at 3p1, that we're looking at aluminum. So we start at 1s, 2s. Our next type of orbital is a d. That's our transition metals. If S starts at 1, P starts at 2, D starts at 3, because it was that little math element from learning about our quantum numbers from the first PowerPoint. So 3D, 4, 5, and 6. There are 5 different orientations for D. Each can hold 2 electrons, so 10 electrons. Let's see how many elements go deep. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Awesome. So this would be 3D10 for zinc, and so on as we go down. Mercury would be 5D10. Awesome. 1s, 2p, 3d. What kind of F is that going to be? We're going to have 4F. Totally makes sense. Obviously, you probably have never really used these elements down here. You might even be looking at a periodic table thinking, I have never heard of that name. We're pretty much never going to touch the Fs. We'll do maybe a little bit of D, but not a ton. Once we get into that part of the periodic table, that's kind of not something you use substantially. We won't be going there. So you're not going to be making electron configurations for something wedged in the 5Fs. So anyways, there is a pretty solid trend going on with this, which makes memorizing all this math a little easier, because as long as we can use our periodic table, you might not have to memorize any math. So these blocks, super easy. Might be something, if you have a printed periodic table, that you might want to color code or at least label a little bit, just to show where the blocks are. Okay, so let's try to use it to find an element configuration of something. And I don't think I have it written down, and that's where the scrap piece of paper might come in handy. So let's look for gallium on the periodic table and kind of try to figure out what we would give for an electron configuration. Let me just make it a bit bigger. So gallium. Gallium is this guy right here. We can see that he's over onto the P block just by seeing its location. And so we know when we're going to get this massive string of numbers and letters is going to end with a P1, right? Because it's the first one in a P. We just have to kind of get through all the 30 elements before it in order to label it appropriately. So, sorry that I don't have a pen and paper or a way to write this, but what we have to do is we literally have to start, because of Aufbau, at the lowest energy and fill it all up. So if we were to look at that last slide simultaneously, we know these are the 1s's. So we'd fill them both up, 1s, 2. We'd fill up the 2s's, 2s2. Here we have the P block, and remember that it starts with 2. So it'd be 2p6, because we're filling all 6. 3s2, 3p6, we're filling all of them. 4s2, and then we get to the D's. Remember, D starts at 3, so we'd have 3d10, we're filling all of them. And then here's our guy that we care about. So that was 2p, 3p, we're now at 4p1. So if I were to say that all over again, and we would write a big string of numbers and letters. We'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. So that would be the entire electron configuration of gallium. And if we're thinking of off-bow, and when we looked at the weird sequence of numbers and we thought, hey, 3D is somehow lower energy than 4p, I said that wrong. 4s is somehow lower energy than 3D, despite being a higher number. It's an easy way for you to remember it because we have to fill in elements number 19 and 20 before we can touch these 3Ds. So it's an easy way to know, hey, when I'm labeling stuff, I need to write 4s before I can write 3D because I'm following the periodic table. So that would be for gallium. So we did energy level diagrams, lots of drawing of arrows, and then you thought, okay, yes, electron configuration, much simpler. But you'll find as you do some of them that it gets super, super repetitive because you're following off-bow, always going to start with that 1s2, 2s2, 2p6, 3p2. And it's a great way to learn it just from all the repetition, but you'll get kind of annoyed by doing the same thing over and over and over again just to figure out what your finishing point is going to be. And that's where this last way comes in. So it's called condensed electron configuration, or sometimes noble gas configuration, because we'll be using noble gases to make it a bit shorter for us. So just because noble gases are stable, they're a full octet, as we saw from Bohr diagrams, it's an easy way to kind of chop off that part, knowing that if we were to make an ion, and if we were to gain or lose electrons, that part won't be touched because we've got stuff to add or lose to make our ion. So how we do an electron configuration is we always look at the most recent noble gas compared to the element we are working with. So if we're working with chlorine, we're right here. Obviously argon is right next door, but it wasn't the most recent one. We haven't passed over argon when we decided to make our electron configuration because it's a higher number, right? We didn't have to touch argon when we went through the 1s2, 2s2 type of stuff. We did bypass neon though. So instead of starting from the very, very start and labeling everything, we can just put neon in square brackets and start from whatever happens after neon. So if we put neon in square brackets, we're now at sodium and magnesium, which is 1s, 2s, 3s. We'd have 3s2, 3p5, because chlorine is 5 in. Let's just double check that I am right. Yay. Okay. So instead of having this huge string, slightly smaller, because chlorine is obviously not too far up, but if we got into a much higher element, that might be in like the 50s or 60s, is probably going to save your wrist a lot of time. SN, one of those weird Latin ones, we're looking at tin. So 5p2, we can quickly figure out where tin is on the periodic table because that's probably one of those things you don't look at too often. You know, when you get into like this middle region, you're scanning a lot. 5p2, here we go, second one in. There's 2p, 3p, 4p, 5p. Our most recently passed over noble gas was krypton. So we can exempt like all of this labeling that came before it. That's really nice. We put krypton into square brackets, which means we don't have to start until RB. So we've got 1, 2, 3, 4, 5. 5s2 takes care of that. 4d10, we go all the way across. And then 5p2 gets us to tin. So it does save us a lot of time by the time we get to much further elements. So that's if we have just a neutral uncharged atom. There's one other thing we have to add to this, which would be ions. So we can either gain some electrons, we can lose some electrons. Obviously, if we're doing electron configuration, they'll have to be shown somewhere. If we're looking at anions, something with extra electrons, that's the nice one, because all you have to do is just like smack extra electrons on. So if we're looking at Br1 minus, we know that Br added an electron to try to kind of look like krypton, right? So we're pretty much making an electron configuration as if it were krypton. If you ever do your own research, it's called isoelectric. So it has the same electron configuration as something else. So if we were to do normal bromine, and let's say we're doing it with the condensed version, and we just do square brackets with Ar in it, which means we don't have to start until we get to K. That's going to be 4s2, going to go all the way across the 3Ds, so 3D10. And then we're into 4p1, 2, 3, 4, 5, 4p5, except we have bromine with a 1 minus charge, which means we actually have 4p6. We're adding that extra electron. So adding electrons, very nice. Just pretend like you're one element over. If you're adding 1 electron, say if you're oxygen and you're O2 minus and you're adding 2 electrons, well, then you're still making neon pretty much. Just add those electrons to the end of your electron configuration chain. It gets a little bit different, and hopefully you wrote down gallium last time we actually did it, when you're taking away electrons, because there's a special way to do that. We need to take from the highest principal quantum number, so the highest n. So the way I do it, at least, would be to write down the neutral way first before taking them away. And so what we've seen, if we're taking away from the highest n, we've seen sometimes that the s's might be higher in n number than the d's, right? Because this is 4s2 and this is only 3d. So if we were to take away from either one of these things, even though the 3Ds are going to be written afterwards, we're going to take electrons away from the 4s's because it's a higher quantum number, higher principal quantum number, sorry. So if we're looking at gallium, right here, that's kind of giving it away a little bit. We are going to have argon in square brackets, then we'll have 4s2, 3d10, 4p1. And we want to take away, I want to say it said 3 plus. We want to take away 3 electrons. We've got a 4p1 followed by 3d10 if I'm going backwards, and 4s2. So we've got 3 electrons in a n equals 4. Despite all of these being written somewhere in the middle, we're going to take away that 4p1 and both of the 4s's. And so if I were to actually write down what I have argon in square brackets, 3d10. And that would be our electron configuration for gallium 3+, because we're taking away from the highest n value. That might pop back up, just FYI.